Step onto a standard elliptical machine, and your feet are immediately locked into a single, unchangeable, one-dimensional track. The mechanical design dictates a highly specific oval, and your body simply goes along for the ride. If you want to take a longer stride or climb a bit higher, you have to force the machine to adapt. You push a button, wait a few seconds, and internal electric motors physically crank the track into a new, but still completely fixed position. Now, compare that rigid system to the Precore Adaptive Motion Trainer. On this machine, a user can effortlessly switch from a short vertical stair climb straight into a wide, aggressive sprint in one fluid motion. Here is the strange part. There are no electric motors inside this machine adjusting the track on the fly. It is built entirely out of a rigid collection of solid metal bars. So how exactly do fixed mechanical linkages instantly adapt to the unpredictability of human motion? Solving this requires mapping the machine's behavior as a system of variable geometry rather than a single fixed track. To find the math hiding inside this design, we need to look past the plastic casing and the user interface. You see that large wheel at the front? Ignore it. It provides the resistance that makes your workout hard, but it has absolutely zero control over the physical path your feet take. Instead, look right at the center of the machine. The core structural framework is made up of a very specific arrangement of swinging metal arms and mechanical linkages. This specific arrangement of pivots and arm lengths defines the entire range of motion available to the user, overcoming the mechanical constraints of traditional designs. This image maps a geometric wireframe directly over the physical machine. Notice the upper arm. Point P travels exclusively along its own fixed dashed circular arc. Meanwhile, the lower linkage, point Q, swings along a completely separate, independent circular path. Because these two pivot points are allowed to swing completely independently of one another, engineers describe this system as having 2 degrees of freedom. Trying to calculate the final motion of 2 independent variables swinging simultaneously is chaotic, so to see what they actually produce, we have to isolate them and run a virtual experiment. Let's start the test. If we mathematically freeze the upper arm, point P, in place, and only let point Q swing freely, the lower arm forces the foot pedal to trace a specific, sweeping, one-dimensional curve. Now reverse the experiment. We lock point Q into place and push point P back and forth to its extreme edges. With the bottom locked, the pedal traces a totally different curve, intersecting right over the first one. Which leads us to the final question. What happens to the foot pedal when we unlock both points, allowing them to swing simultaneously? Looking at the solid red sheep in this image, you can see the result. By unlocking both variables, the pedal breaks out of a single one-dimensional line. The infinite combination of those swinging arms colors in a solid, 2-dimensional shape. This red area represents a mathematical envelope containing every physical coordinate the pedal can reach. A short stride traces a small circle in the center. A stair climb draws a vertical oval. A sprint stretches outward, grazing the outer borders. The resulting motion feels intuitive, responding to the user's intent through pure geometry. By adding that second degree of freedom, the design stops dictating the path and instead defines an open space for the user to navigate.